Thanks for sticking to the very last lecture. So I'm an experimentalist, and then over the past 2-3 days, you've heard of this term, fractional Chern insulator, on and off. And what I hope to do today is to tell you about, I wouldn't say the history, but roughly how these, how experimentalists, with the help of theorists and back and forth, how we came to realize and experimentally detect fractional Chern insulator. And the really fertile ground for the detection and realization of fractional Chern insulator is really moiré flat band. So I just want to remind everyone, about the fractional quantum Hall effect that we heard about from Mike Manfra. It was first discovered in 1982, and the idea that came as a surprise, but later I think there's a very easy way to understand it, at least at a superficial level, which is if you can have the integer quantum Hall effect, which you can get by taking, say, a two-dimensional electron gas and subject it to a large external magnetic field, then you get integer quantum Hall effect. Then if you, in the presence of strong electron-electron interaction, then you will be able to get a fractional quantum Hall effect. And that was a kind of a big breakthrough which revolutionized our thinking. So, the concept of topological order and then the excitation in this case is they carry fractional charges, and then they have very weird exchange statistics, and there are other composite fermion theory, pairing state, et cetera, et cetera. So the first discovery was in 1982. So now if you do the math, it's been 40 years. And as you heard from yesterday and the day before, fractional quantum Hall effect is still a very vibrant research field. And one of the things that people, for example, are really working hard to realize is what's called anionic braiding. And you already heard about this in the last 2 days. Another thing I just want to quickly mention is people, in addition to anionic braiding, another thing that I appreciate a lot is people try to use fractional quantum Hall effect, which is already quite exotic, and try to combine it with some other materials, some other property in order to create even more exotic physics of matter. And here is an example. There's an object called parafermion, and this is something that you could get if you interface fractional quantum Hall effect state with superconductivity. And then this is one attempt where they basically put graphene and then interfacing it with a superconducting contact. So about 10-15 years ago, people started to think about, can we relax the condition by which we realize, objects that look like fractional quantum Hall effect. And that's the subject of today's lecture. It's called fractional Chern insulator. And that, as I already discussed, for fractional quantum Hall effect to happen, you need Landau level, and then you partially fill it, and you hope the system have strong electron-electron interaction, then you'll be able to get fractional quantum Hall effect. And now, if you want to realize fractional Chern insulator, the starting point for that is to find basically a lattice or some material. At zero magnetic field, the band structure is described by what's called a Chern insulator, or they're described by Chern band. It looked almost like Landau level. The only difference is that you don't need external magnetic field, and the magnetic field is actually provided by the topological property of the electronic wave function. And now, but you can immediately draw the analogy if you are able to partially fill this Chern band, and in the presence of strong electron-electron interaction, you might be able to realize a fractional Chern insulator. And the reason why the community was super excited about this topic or this state is because of several reasons. And here I listed 3. The first motivation is that you might be able to hope for realizing high temperature topological state and topological order. And the reason is because here in a lattice, if you think about the energy scale, just simply E over A, E squared over A, then the Coulomb energy can be very, very large, whereas for the other one is determined by the magnetic length, or the 1 over square root of B. And the other thing that's quite exciting is, compared to Landau level, which can be viewed as a very special case of Chern band with a Chern number of 1, a generic Chern band or the system, they can be characterized by a Chern number that's greater than 1. It can be 1, it can be 2, it can be 3. And what's really exciting about this is that if you can realize a material system that's described by, say, Chern band with Chern number greater than 1, 2, 3, 4, then anything that you're going to realize, it will be very different from what's being observed and seen in, say, the fractional quantum Hall effect. And the last motivation I want to mention is that I already discussed, people try to realize this object called parafermion. And in order to do that, you need to interface fractional quantum Hall effect with superconductivity. And we know superconductivity doesn't like magnetic field, and in this case, fractional Chern insulator, by definition, they should exist at zero magnetic field. So they should be readily compatible with superconductivity. So the starting point is really to find a material system that's described by Chern insulator or Chern band. And there's a very famous paper by now, it's called the Haldane model, where Duncan Haldane considered actually what he called 2D graphite or honeycomb lattice. And then if you have the proper hopping term, then you will be able to realize this basically at that time called Landau level without magnetic field. And in 2013, a group in China, Chicken Xie's group, they were able to realize for the first time, at least to my knowledge, the Chern insulator. And to do that, they basically took topological insulator thin film and then dope it with magnetic dopant to break the time reversal symmetry. And in the context of fractional Chern insulator, this is a good starting point, but there's one key missing ingredient, which is the Coulomb interaction. In this particular case, the electron-electron interaction is weak. Therefore, they were only able to observe the quantum anomalous Hall effect, but there's no fractional feature. So one key ingredient missing is really electron correlation. And as you have heard over the past few days, one way to do this is really to engineer electronic bands that are extremely flat. So today's lecture, I'll basically walk you through this time axis and then go through how people, what were the logic behind this discovery, and then I will actually focus a bit more on the technical or experimental progress, how the experiment was done, how the material was discovered and engineered, and then what was the technical advancement that enabled this discovery. And then the first discovery of something that can be thought as a fractional Chern insulator was back in 2017. And then at that time, FCI, the eligible FCI required 30 Tesla. And maybe some of you would argue that in many samples, for example, gallium arsenide, I don't need 30 Tesla in order to get fractional quantum Hall effect. But I'll try to argue that this is still something interesting, and then we learn a lot from that. And later in 2022, we did this experiment where we discovered FCI in another material platform, but it still requires what we argue as small magnetic field of the order of 5 Tesla. And then it was briefly mentioned yesterday during Eve's lecture. Last year, there was a very exciting time for FCI because there were 2 reports in 2 very different material systems where people discover FCI as strictly zero magnetic field. So as I said, what I'm going to do is basically to go through this time axis, and then probably it will be influenced by my personal experience and taste. So I hope you don't mind. So before I do that, I want to just quickly give an introduction of how, at a very high level, how can we characterize and how can we experimentally know we can have FCI. And one very important concept is the Chern number. And it's maybe not a rigorous definition, but if you can find a state that's characterized by a fractional Chern number, in some sense, then you have something that looks like fractional quantum anomalous Hall state, fractional quantum Hall state, or FCI. And maybe the most familiar way to many of you is measuring what's called the longitudinal resistance or resistivity, and which is characterized by, it's a direct measure of the Chern number. And for example, in quantum Hall state, if you, this is a case in graphene, you see that this line, you see a lot of plateau, and each plateau basically corresponds to different states with different Chern number. And this is usually done, this has to be done using transport measurement. And a second method that some of you might not be that familiar with is using what's called the Strader formula. Basically, if you can identify a gap state, incompressible state, and then examine its evolution as a function of carrier density and magnetic field, because actually this state, you need to, they have flux attached to them, and then you actually need to compensate the electron filling. And in practice, what you do is really just to look at either through longitudinal resistance or XX, and then look at sweep magnetic field and gate voltage, and then look at this linear trajectory. And as I will tell you later, this can also be done by monitoring other kind of quantity, for example, compressibility, which actually is quite useful sometimes. And in particular, for the second method, it requires, as you will see, it requires less good of a sample quality, especially when the community is not able to make good quality sample yet. Yeah. So let me start with this experiment from 2017. Or actually, the concept date back, as you see, 1960s. So if you want to make a Chern band or a topological Landau level, but subject to a lattice, a very straightforward way of doing this is just literally take Landau level, cyclotron orbit and Landau level, and then say, oh, I just insert a lattice beneath it, then the resulting electron, the electron in this system, in this case, they will feel at the same time the Landau level physics. So, it's extremely flat band. And at the same time, they feel this periodic potential that will get modulated. And this problem, people actually thought of this problem back in the 1960s. And later, I think after computing power become available, you can actually calculate the energy spectrum of this problem. I think now you can even easily find code on GitHub or something that allows you to do this on your computer. And here, the x-axis is the magnetic flux, or in other words, the lattice spacing in your periodic potential over the magnetic length, and then take the square. And the y-axis is the energy, and this is often called Hofstadter butterfly, because Hofstadter is the person who compute this for the first time. And if you have good eye, you can maybe recognize some butterfly shape in this spectrum. And now going back to the Chern band, what's remarkable and what the reason why this attracted so much attention in the community is that if you compute the Chern number of this spectrum, what you will find is that you can actually color the spectrum whenever you have a gap, whenever you have an empty space, then you just compute the total Chern number of all the field bands. And then what you will find is that they're all very colorful. What that means is that all these empty space, if you are able to position yourself there, then you actually have a Chern insulator in some sense. But again, this is, it's a little bit Landau level physics mixed with block wave function. But this is already a very good starting point, at least at that time. But one key issue is that for most of the material that you have, you are on the left-hand side of this axis. And the reason is because the crystal that we have, or the thin film, say gallium arsenide, all that we have, the lattice constant is of the order of Angstrom scale, less than 1 nanometer. And if you want to go to this, colorful region, that where color change very abruptly and frequently, you actually need thousands of magnetic field, and which is not achievable, at least with the current technology. So you see that if you cannot really change the magnetic field to compensate this, but you still want to get access to this colorful region, what you can do is to maybe find ways to change the, the lattice constant. And one way of doing this is to use moiré superlattice. And the first moiré superlattice that I'm aware of is when you place a graphene on top of boron nitride, and because of the closed lattice constant between the two material, but not quite the same, you would always get a moiré superlattice. And then this, there was a series of experiments back in 2013, which look at this. And then if you make this sample and then look at it under, say, atomic force microscopy, you can, the resolution is not great, but you can see that there is some periodicity. And you can actually create, using this way to create an artificial lattice that's a long wavelength periodicity, 14 nanometer. And then if you now go back and try to convert the length scale, if you want to go to the colorful region, you only need a magnetic field of the order of 25 Tesla, which is achievable if you go to National Lab, high magnetic field facility. And just one comment that will become useful later, and it was mentioned yesterday during Yves' lecture, is that the alignment to the HPN for graphene, it will change the electronic property of graphene, because there's this what's called a mass term, sublattice term, which will open up a gap. And then indeed, in this experiment, they measure the resistance of this kind of sample and then look at the temperature dependence. And indeed, at the charging neutrality, there was insulating behavior. So I would say the more direct way of confirming the Hofstadter, the length scale, when you look at the AFM image and all that, it makes sense. But the more direct way of measuring and confirming you really have a Hofstadter problem is to find features that are explained or described by Chern gap. And here's what they measure. They measure the sigma XX, so and the sigma XY. You can see that at low field, around 7 Tesla, you just see the plateau. It always goes the same way. The 4, 2, 0, minus 2, minus 4. And starting, when you start to approach like 20 Tesla, weird thing happen. Somehow the minus 4 plateau become wilder. And it becomes even wilder if you go to 30 Tesla. And this is already telling you have some anomaly happening. Now, if you look at the field sweep, where sometimes called the Landau fan, you see that you can actually analyze these lines using what I told you about the Strata formula. And what you can see is that you have your normal quantum Hall state that are marked by the white linear lines. In addition to that, you actually have other lines that are linear and then intercept at some number. And the reason why you have 3 minus 4 plateau is because you actually have 2 new states that are enabled by this long wavelength moiré superlattice. And there are ways to characterize this. You can actually convert the density and then knowing what for example, the size of the moiré superlattice is. And it turns out that, for example, for the yellow line, it corresponds to a state that look like the minus 4 quantum Hall state. But in addition to that, you actually need to add some electron because you have a periodic lattice. And the number of electrons that you add into the lattice is precisely, on average, 1 electron per site, super lattice site. And then for the red one, it's very similar physics, but now you actually need 2 electrons on average to the moiré site. So this is a good exercise, and also this experiment tells us that it has all the ingredients to realize, you can go to these colorful patches of the Hofstadter spectrum. But at this point, there's no fractional state. And later, in 2017, 2018, there's this new experiment done at UCSB by Andrea Young's group, where they make two changes. The first changes that I won't go into the detail is that they replace the gate material, instead of using gold, which turns out to have many facets if you deposit it using an evaporator, they use a graphite, which is much flatter, has much lower charge disorder, and it turns out to improve the device quality by many, many times. And the second changes or the advancement they made is to, instead of measuring resistance, they measure what's called a capacitance. So the device geometry that they fabricated, it looks like this. So you have a top gate, and then you have your sample of interest, bilayer graphene aligned with HBN, bilayer because it's more tunable. And then on the bottom side, you have another graphite. And the quantity that they measure is capacitance, and more precisely, it's called the penetration capacitance. You can think of it as if you apply a small AC voltage, it can be larger here, and then try to sense the electric field that the top gate can feel. Then you can immediately guess that it would depend a lot on the electronic property of the bilayer graphene sample that you have there. Just to give you an example, if this layer is very compressible, and bottom you have an electric field trying to, field line will try to go out, then when you have a metal, then the electric field will get screened out. So the signal that you will get when you measure the voltage on the top graphite would be very small. And on the other hand, if this sample is insulating or incompressible, then it almost behaves like nothing, or vacuum, right? So what you will get is close to just two parallel capacitance plates, which is not screened. So by measuring this capacitance or penetration field capacitance, you can easily tell whether the system is in a compressible or in an incompressible state. And one advantage of this is, compared to the transport experiment, is that it doesn't require a complete current path, say from electrode A to electrode B, and it's also less sensitive to disorder, because you don't always need to make a super qualitative statement. For example, if you see a spike in this penetration field capacitance, that it means that you already have an incompressible state. And then you can use what I call the method to look at the evolution and then analyze those trajectory, and already you will be able to make a claim. And they did that, and this is the data they see. The top row is the data, hole dope side, electron dope side, and then what you see is that there are a lot of linear trajectory. Some are stronger, some are fainter, and then what you can do, and that's what they did, is to analyze this linear trajectory. And the way to analyze this is looking at the slope and the intercept. So the slope tells you about the Chern number. You remember I told you if the Chern number is fractional, then you have something like fractional quantum Hall effect and fractional Chern insulator. And in this case, and then the intercept is telling you how many electrons you are attaching to the periodic potential or the lattice. And by that, you can classify all these states. In particular, there are a number of blue lines that have fractional intercept and fractional slope, and that will classify as a fractional Chern insulator. But you see that this is very different from what Haldane proposed. The starting point is not really a material that's described, with a complex hopping term, etc., and then get an energy band that's described by, a Chern band. And here, you can think of this Hofstadter problem as interference of Landau level. So that you still need magnetic field to generate this Landau level, which give you, in some sense, the topology. The topology here is not intrinsic. Therefore, if your goal is to realize that the true FCI, what you need is, this is not going to work. This is nice, and then there are a lot of interesting physics that you can probe, but this is not enough. So that's in 2017, 2018. So how can we find a material system that has flat Chern band? I guess by now we all know the answer, and yesterday's lecture actually introduced already this material system, twisted bilayer graphene. That was this big deal in 2018, and you already heard about that yesterday. And for the purpose of this talk, what you need to know is this system is described by these Dirac cones, and all the symmetries are preserved. And you have 4 of them because you have spin and Vallée degeneracy. And Eve told you yesterday, if you are able to break some of the symmetry, for example, break the C2 symmetry, which can be done by aligning the sample with the hexagonal boron nitride, then you can actually gap them and then to generate bands with finite Chern number. And then this was immediately recognized soon after the discovery of correlated state superconductivity in twisted bilayer graphene. And I think 6 months later, there was this experiment again from Andrea Young's group where they indeed take twisted bilayer graphene and try to align it with HBN. And then at the moiré filling of 3, they observed this quantum anomalous Hall effect, which is a strong evidence. It's basically telling you that the system is really described by Chern bands. And then because of electron-electron correlation, you can basically stabilize a Chern insulator. And later that summer, 2019, there were a series of work that was mentioned also yesterday, where if you apply a small magnetic field, you can also stabilize a similar state. And at that time, I was a PhD student doing scanning tunneling microscopy, and then in Ali Yazdani's lab at Princeton, and then we did one of the first tunneling experiment into twisted bilayer graphene, and you see these features, red lines, and then x-axis is energy, y-axis is gate voltage. Basically, you are trying to tune those flat band and try to push them to the Fermi level, and then you do spectroscopy, look at how the density of state evolve. And the bottom line here is that when the flat band is near the Fermi level, there is some anomaly that happens. There's somewhat, for example, one of the band will suddenly get broadened by a lot, and that's actually provide us a measure of the energy scale. Like what at the 0th order, for example, what the Hubbard U is, or the Coulomb interaction is. And then you can also compare with the bandwidth measuring characterized by the width of the tunneling density of state. And you see that, and you heard, I think, from Ming, if you want strong correlation, then you want U larger or much larger than W, and it looks like we are in good shape here. So at that time, I think MATBG was probably the most promising candidate if one wants to look for FCI, because it has Chern band, it has strong electron-electron correlation. And at that time, I was about to finish my PhD, and I was thinking, what should I do? I've been following FCI for quite a while, and it sounds like this is a very exciting place to jump in. And it's even more assuring when you have, theorists, looking at this problem. And there was, this paper were actually all posted in 2019. And what they did is to look at the twisted bilayer and align with HBN, and then try to look at what the ground state is if you try to fractional field, partially field the system. And I think this is the ED calculation that one of these authors did. And what you see here is that there are exactly 3 states here that's separated by energy gap. And I think they also did entanglement spectrum look at, it's really 1/3 fractional Laplace state. And in addition, they also look at how robust this energy gap is, because at the end of the day, if you want to detect this, what matters is the energy gap. And it looks like the energy gap is not too sensitive to the model parameter. It's about 1%. Now, the knowledge I have at that time is, I showed you in the previous slide, U is about 25 millielectron volt. Then what that means is that if you have perfectly clean sample, so in the zero disorder limit, then the gap for the FCI, at least for the, in this case, 1/3, it should be 250 microvolt. And if you convert to temperature, it's a few Kelvin, but in real life, you always have a lot of disorder. And it's actually, the disorder is actually even more complicated here. So I thought if you really want to do this, then you need two things. I told you about the capacitance. Capacitance seem to work better than transport if you want to detect this kind of state. And second, you want something that's local. So that's what I did. I moved to Harvard to learn this technique called scanning single electron transistor. I'll walk you through what this technique does, because this is a very special technique only 3 and actually 4 groups can do. So the concept is you have this very sharp tip, and then using some procedure, we can fabricate actually a very, very small quantum dot right at the apex. And the apex is around 50, 100 nanometers, so it's a nanoscale probe if you are being generous. And the way we operate this probe is, quantum dot, if you try to monitor the transport characteristic across this, what you will see is Coulomb blockade oscillation every time, because every time you can only allow one electron that tunnels in. And in practice, you see that if you are able to place yourself here, any small change of external electric field would cause pretty large change in the SCT current. So that means that this is a very good electric field sensor, and then you can use that to measure electronic compressibility and also detect incompressible state. And just as an exercise, if you have a system that's described by this kind of denser state, with an energy gap, what you will measure in electronic compressibility, usually the x-axis is carrier density, and what you will measure is a spike, because the system is not compressible. And it's very similar to the capacitance measurement that I introduced to you. So it sounds fairly easy. Wherever you have a spike, you identify incompressible state. And what's even better is that this is actually a very quantitative measurement. It provides you a direct measure of what's the energy gap. As you heard from Mike Manfred, this is actually a useful quantity if you say want to build an interferometer and do other stuff. And I want to spend maybe 2 minutes telling you SCT is actually very useful. The first thing is if you have a sample, say fractional quantum Hall or fractional Chern insulator, if you have a scanning SCT, you don't need interferometry, you don't need to do noise measurement. What you need to do is to go in and then try to scan and then looking at the charging event of the sample. So here, this is a very old experiment done like 20 years ago, looking at the gallium arsenide quantum Hall state. On the left-hand side, you see these black lines. That's that's like a pocket. That's for a measure for the nucleus 1 state. And then now, if you do the same thing but tune to nucleus 1/3, it's a bit hard to see, but you see that there are many, many more charging lines. And there are many, many more lines. And actually, these correspond to charging event of electron or quasi-particle, depending on what's the excitation in the system. And just by counting the number of charging events, if you have a reference, say the integer state, you can immediately say, looking at the right plot and compare it with the left plot, the quasi-particle charge is precisely E over 3 with almost no error bar. And this can be very useful. And because this is, I said, this is a thermodynamic measurement, you can actually use Maxwell equation and then to extract, say, entropy and monetization. And you can also use this to measure image electron transport without using contact or using minimum contact. And people have done this, try to image ohmic transport, ballistic transport. You can even do hydrodynamic transport where electron flow like honey in a cup. And we recently also developed a way to measure the chemical potential of magnon, but in a strongly interacting electronic system. So for this talk, what you need to know is we're going to apply this, and we apply this as a way to measure the local Chern number. And this is using the Strader formula that I discussed. And this is a characteristic measurement in bilayer graphene, I think, that was done again 10 years ago. And then looking at this line, slope, and intercept, you can deduct whether you have a fractional state. And then we apply this to measure angle twisted bilayer graphene. To our very surprise, the very first sample, it just worked. I don't have more to say. I guess it's good. So this is the data we got in 2020 actually. So you see there are a lot of features. I forgot to put a same plot, the plot of the transport property of the very same sample. You see nothing there. And here I forgot the number, but you see like a dozen of states. And it's very, very rich. And you can go ahead and then do the analysis I told you about, and then you can go about and characterize them and then see what, what's the slope, what's the intercept, etc. And then we found in total 8 FCI. But you see that we still require a small magnetic field to do that, and I'll discuss a bit more about this. And I want to take maybe a few minutes to walk you through and then tell you about what's the lesson we learned from this. And to do that, I'll first focus on carrier density between 3 and 4, because that's a place where we understand the system better, because the system can be well approximated by just one single Chern band. So this is what the low field portion, zero magnetic field, and then we see a number of states that have fractional intercept, and however, they either have no slope or they have integer slope, and that's not what we want. And I think I'm running out of time, so I'm just gonna quickly say that yesterday it was mentioned that because you have this strong density of state modulation in real space, you actually have a strong renormalization of your energy band. It's called a Hartree term. And then a lot of sketch that I drew to you, and also it was drawn yesterday, the energy band are supposed to be very, very flat, at least at a very single particle level. However, in real life, because of the Hartree potential, you will actually have bands that has, say, deep at the center of the Brimman zone. And at the same time, there's this concept of Berry curvature. Although a band is topological, when you integrate the Berry curvature, you get an integer Chern number. However, their distribution over the momentum space need not be homogeneous, and usually it's not homogeneous. And as you see, this is a problem for FCI. But the point here is that at low magnetic field, we see states that break translation symmetry, and depending on how you fold the bands, you will get different states. And the more exciting thing is when you increase the magnetic field, you see that these vertical states, they just abruptly disappear, and instead they are replaced around 5 Tesla. They are replaced by states that have slope. And you can actually compare already the slope with the very broad red feature there, which is an integer state. When we had the data came in without really analyzing it, we knew we are up to something, because the slope is very different, and it's between 0 and 1. It got to be fraction. And when you do the careful analysis of the slope, we found that one of them is 2/3, one of them is 1/3. And these are very familiar number for us, when you talk about, say, fractional quantum Hall effect. And so we argue that this is a FCI state because the system is very different compared to, say, the Hofstadter problem that I discussed. It's described, for example, people saw quantum anomalous Hall effect at Nichols 3. So it's intrinsically, they have their own flat Chern band. And we were quite happy because the magnetic field is, at least in our view, substantially smaller compared to what was needed for bilayer graphene aligned with HBN. And you can also try to back up what's the slope, what's the intercept, if you look at this very carefully. And as I mentioned, the one unique strength of scanning SET is the ability to directly measure the energy gap. and which is shown here for many of the states. And for the fractional states, basically are those that are marked in green and yellow or orange. And we can go ahead and characterize what's the number. You remember the prediction was 250 microvolt. And in practice, what we measure is here the change of chemical potential is around 150 microvolt. But there's a little subtlety here. The subtlety comes from when you want to estimate the energy gap for this kind of quasi-particle excitation, then you actually need to take into account by the effective charge, the quasi-particle charge, which is in this case, if it's 1/3, the natural assumption is E over 3. And then you actually need to divide that number. So the estimate that we got is 30 to 70 microvolts, around 0.6 Kelvin. And you can imagine it could be quite challenging for the transport experiment, especially it was mentioned yesterday, all these samples, they have actually a lot of what's called a twist angle disorder. So here I'm just showing you the ED estimate again. If you take the number that you will get in the perfect case would be 250 microvolt, but in real life you have a lot of things that you don't want. So I already alluded to this, why don't we see FCI as zero magnetic field? And the reason is because this Berry curvature distribution is not homogeneous. If you think about, say, the Landau level, because the energy level is extremely flat, then no matter how they distribute in the momentum space, then it doesn't really matter because it's homogeneous. However, in this case, it's not quite that, and that's the reason why at low magnetic field we see charge density wave either trivial or topological, and we need magnetic field basically to help flatten this distribution so that the system behave more like Landau level. And you can do this, confirm this with calculation. Basically, you can look at the exact organization, what ground state you get, and then you can, that's how I color this plot. On the left-hand side, you get FCI, and then on the right-hand side, you get CWA. Here, the x-axis is this tunneling parameter between layer called W0 over W1, or that's decided by the relaxation. And for the red circle, what I drew is basically data points that you will get if you are to compute the Berry curvature inhomogeneity of your energy band. And you can try to look at how this changes as you change the magnetic field. Basically, you look at what's the Berry curvature distribution as a function of magnetic field. And then because as was mentioned yesterday, this tunneling parameter is not quite known. So we can only say this is the range. But the good thing is, it looks like the calculation is not too sensitive to exact value of what you get. And then if you look at, be generous and then say it's between 0.6 something to 0.7 something, then the range you will get, going from CW to FCI is around 0.2 flux quanta, and converted to magnetic field is around 5 Tesla. Because it was brought up yesterday, I just want to quickly mention because yesterday I think Eve mentioned ways to extract that from a numerical or theory point of view. I just want to mention 2 ways that some people think allow you to extract this W0 over W1. Of course, I'm biased. The best way is to use STM, but it's still not very perfectly correct, is to look at the area, this bright region. Basically, you have the A atom in the top graphene layer and the A atom from the bottom graphene layer stacked right on top of each other. And then you have the AB region. And then in practice, depending on the angle, etc., and the relaxation, the area of the bright spot would be very different if you had different relaxation. So one way to approximate this is or extract this is just to take the area of AA divided by the area of AB and BA, which is the dark spot, and then you can get a number. And then our estimate was 0.83. And later, there's another paper that used a completely different method. The essence of that is, if you look at the energy band of twisted bilayer graphene, you have this high energy band color in red. It's dispersive, and then you see there's this crossing point that look very much like a Rashba band. And actually, that level of splitting is determined by this W0 over W1. You can check out the paper if you are interested. And the point is that if you now look at the Landau level of the dispersive band, what you will find is that the Landau level has to cross because you kind of have two bands, right? And then you have the two band already crosses, and then if you are to compute the Landau level spectrum, it would look very, very different. And experimentally, this is something that one can easily measure. Whenever you have a Landau quantum Hall state disappear around that filling, then you know that's the crossing point, and then you can basically experimentally determine this, and then back up what's the W0 over W1. So before I go to the more recent work, I just want to mention in twisted bilayer graphene, I only talked to you about what happened between nucleus 3 and 4. Actually, we also saw a number of states. This is just a quick summary of that. Basically, all the red lines, orange line that you see here, they have a fractional slope. And some of them we can try to understand, make sense of the intercept and also the slope. And sometimes they seem more exotic. It requires arguments such as, oh, I need to break the translation symmetry in order to make sense of the intercept and slope. And there are some of them, we just don't understand them at all. We don't know how to characterize them yet. The only thing we know is that they exist, and some of them seem to have even denominator, which I would say it's a prerequisite for finding something exotic. For the rest of, 5-7 minutes, I just want to mention the more recent work. In parallel, so far I focused on twisted bilayer graphene because that was the most understood and most promising material platform. But in parallel, there are a lot of people in the community are also trying to explore, say, moiré superlattices using other material, in particular transition metal dichalcogenide. And there were a series of papers. The first paper, I think, was this one back in 2019, where they predict that if you twist transition metal dichalcogenide, in this particular case, molybdenum telluride 2, then you will be able to engineer topological band, and this, they actually argue you can get TI with this. And later, there's a more formal theory that claimed that in 2021, you can have zero field fractional Chern insulator if you twist transition metal dichalcogenide. I don't remember if they specify the material. And then around the same time, there's also another work from MIT proposing that if you twist WSC2, then you can actually have a fractional Chern insulator. So people have been trying because of, that already after the first prediction back in 2019. The first material system that people try is to take MOT2 with WSC2. There's some reason about band alignment, etc. And then it was mentioned yesterday, you have the two layer would have their own band, but they are pretty strongly localized. And in fact, what matters is, for example, in this case, only the top green band and the bottom orange band matters. And for those who are interested or are familiar, the people argue that this kind of material system realized what's called a King-Malay model. And this is the way I like to think about this system. If you have, say, two bands, and because you can, in practice, you can apply displacement field, because of the star shift, you can actually change the band energy. So it's very much like the TI, in macular telluride. You can, in some way, change the band alignment such that at some point you have a band inversion such that you will find something interesting. So people fabricate these kind of devices, and then indeed here they measure longitudinal resistance and also RXY as a function of filling factor and also displacement field. And the thing that I like you to look at is this nucleus 1 lines. It's a little bit tilted. It starts with a red that's insulating, but trivial. And at some point, suddenly RXX become negligible. And if you, at the same time, at that region, RXY become more or less fixed. And that's telling you you have a new state. Now, if you swoop, I guess, park there and then look at the Rxy as a function of magnetic field, you see hysteresis, which is telling you it's spontaneous symmetry breaking, and also you have finite Chern number. And the sad news there back in 2021 is that in this particular material system, there's no FCI. And later, people explore other material system. I mean, people actually explore that before 2020, I think. And then the result only came out in 2023. This is work from University of Washington, where they look at twisted MOTE2. And the first experiment they did is what's called the trion sensing. You can think of this, for the student who are not familiar with this, trion is basically electron and hole plus an electron. So there's 3 charged particles, and they can be coupled with optics, and that's why you can do photoluminescence with it. And you can think of it, the detailed process of how this interact with the charge carrier in the system is not well known, but it's commonly believed that and taken as a proxy for the capacitance or the dielectric environment. So whenever you see some discontinuity, people think that, oh, I must have, I go from compressible state to incompressible state, and you see that this preliminary, this measurement already tell you that you have something interesting happening at, 1 electron, 1 hole, and then 2/3. And later, they expand this experiment to as a function of magnetic field, and then you can see that there are features, there are 3 features, and then each of them, they disperse as a function of magnetic field, and careful analysis tell you that the leftmost one is -1, and then it's -2/3, and then -3/5. So it means that, and then the really exciting thing is all these data points, they, at least for the 2/3 and -1, they interpolate, they persist down to 0 magnetic field. So this is already a good sign that you have FCI as 0 magnetic field. And of course, the most direct evidence comes from transport measurement, if you can measure Rxy. And I just want to mention that this is highly, highly non-trivial, because a transition metal dichalcogenide, it's hard to make contact with. And then you see in this device geometry, they had to, for example, add another layer between the top and the second transparent layer, which is the boron nitride, because you need to have an additional layer of gate to gate the contact so that you can allow current going from your electrode to the sample and then reach the other side. I will skip this. The bottom line is that they saw hysteresis, which is a smoking gun evidence of fractional quantum anomalous Hall effect or 0 field FCI. And even more excitingly is a few months later, the group from MIT, they found that if you take a completely different material, 5 layers of graphene, or 5 layers of graphene, stacked in a very particular way called hombohedral, which means that every time you stack this, you just shift half of a unit cell to the left, and you keep doing that instead of coming back. And this is in contrast to what's called the Bernal, which basically every 2 layers it go back to the same place. And these phenomenologically, things look extremely, extremely similar to what was measured in twisted MOTE2. And of course, this is the hysteresis. One last thing I want to mention is that now, in addition to discovering 0 field FCI, they also saw some anomalous behavior at what's called a half filling. And this actually attracted a lot of attention in the context of fractional quantum Hall effect, because there's this notion of composite Fermi liquid and more exotic stuff happening. And again, the phenomenology strikingly between these 2 distinct material platforms just look very, very similar. There's hysteresis, there's no charge gap, and at this level, it seemed to be consistent with composite Fermi liquid, and then people are working on that. I just want to say maybe 1 more minute, 2 more minutes. I give an outlook. The stuff that I talk about, these happen over the last 5 years, or even less. Especially the very last results, it's really like half a year, a year ago. So I think this is a very exciting time, and then immediately you can think of basically what should we go next, and where can we go? You can immediately think about, can we just do all the trick that we did, I mean the community did it, and the community know how to do, now just repeat it, for fractional quantum Hall effect, now repeat it with FCI. For example, I mentioned you can interface fractional quantum Hall state with superconductivity. It was a challenge back then, and people managed, and now you have SCI at zero magnetic field. It should be much, much more straightforward. Of course, there's other technical issue, how to make good contact to TMD, but graphene, I think, should be good. And Mike told you about the interferometry. There's also a lot of subtlety there, how to make the dot size, what's the barrier. But one advantage of, say, 2D material, he also mentioned, is the proximity to the gate, which can define very sharp potential, and maybe the bulk edge scattering and all those would be more optimized here. Of course, in this material system, there's still a lot of work to do. We need to understand and characterize a lot of things. And one big dream, two big dreams, at least to my taste, is can we find non-abelian state? Can we find something that look like, say, the 5/2 in the fractional quantum Hall state? So far, all the states that have been observed, we are basically, it's exciting, but we are only reproducing the Laughlin state or the gene sequence, odd denominator, 1/3, 2/5, et cetera, et cetera. Can we do something more, find something more exciting? And then even more exciting, and then I use that as a motivation, is that Chern insulator, they can be quite different from Landau level because they allow higher Chern number. So can we find FCI in system where the Chern band are described by higher Chern number? Actually, there's already some work, not fractional yet. This is a work, again, from Longju's group, where they take 5-layer graphene, interface it with transition metal like WSE2. They were able to find quantum anomalous Hall state with Chern number of 5. So I think, every time you want to find FCI, you first need to find CI. And I think this is a very good starting point. And I'm quite hopeful that this and other material platform will allow you to find more exotic stuff. And I just want to end by saying this is a very exciting time for both theorists and experimentalists, and especially for students. There's a lot of development, rapid development. Every few weeks, there's new stuff coming out. Sometimes it's even hard to catch up what's going on, especially for theory, I would say, as an experimentalist. And I just want to throw out some very trivial question that needs answer, both from the theory side and experimental side. For example, on the theory side, what's the mechanism? How are we getting fractional quantum anomalous Hall state in these two distinct samples? There must be something very, very common between these two that I think as a community, we don't have the clear answer to that. And there are a lot of phase transition that I didn't get the time to mention. And of course, can we get some theory guidance of how to engineer non-abelian state in this kind of setting? And on the experimental side, we need a lot more information. What's the spin structure? What's the energy gap of all these states? Maybe we need local probe, like the one I did, and there are other local probe. Maybe we need to perform spectroscopic measurement. I didn't mention, but some of these material systems, they persist to higher temperature. And the fact that you don't need magnetic field, it can be compatible with RPES. I know people are working on that. And can we, on the experimental side, can we find new material platform? So again, to conclude, this is a very exciting time for students to come into this field. And I thank you for your attention. You mean other than interferometry? Yeah. Can you use the electronic? To my knowledge, interferometry is the most mature way. Because at the end, if you think really big, say non-abelian anion, you want to exchange them, right? Then what are the good way of exchanging them just swap them, and interferometry it's a good way. Yeah.
So transport signature, what is it? Quantization or is it?
It's quantization at the right value, and also hysteresis it's important because it tells you it's spontaneously the time reversal symmetry is spontaneously broken.
You might fraction that. So what's the degree of quantization?
Oh, yeah. Which one you want to attack?
The transport, the tier.
Yep. So I mean, maybe okay. Now maybe this one it's more clear. You see that the blue line is the RxY, but we know if you really want to do this quantization game, what you need to measure is actually invert this and then get sigma xy and sigma xx. And if you want to get really good sigma xy, you want Rxx to be 0. And you see that here Rxx is of the order, I think, tens or 100 kilo ohm. And so it means that it's nice, but it's not there yet. But one comment I do want to make is, if you remember my very first slide, the fractional quantum Hall effect back in 1982, the Rxx is worse than this one. So the residue Rxx, the imperfection back then, it's not as good as this one. So I'm hopeful that it took, I don't know, 10 or 15 years to optimize that for gallium arsenide and all that. And here this was just discovered last year. So I think there's a lot of chance that we can catch up.